Good morning. I'm Alexandra Moore from the Paleontological Research Institution in Ithaca, New York, where we've been working in collaboration with Prince George's County Public Schools since 2018. Today's workshop launches the third year of our NOAA-funded project, A Watershed of Trees. I'm going to begin with a quick experiment. We'll use an infrared thermometer to measure the surface temperature of the leaves of this basil plant sitting in my kitchen window. You can see that the temperature is 78 degrees Fahrenheit. If I turn the thermometer to the shiny white IKEA cupboard right next door to the plant, you can see that the temperature is higher, 82.2 Fahrenheit. Why do two adjacent surfaces have different temperatures? The reason is that the plant is actively transpiring water through its leaves, and the transition from liquid water to water vapor causes evaporative cooling of the surface of the leaf. We'll keep that in mind as we consider other aspects of our watershed of trees. So let's start really big. And through the workshop, we'll zoom down to some of the everyday details that make a successful course. Atmospheric greenhouse gases absorb infrared solar energy, keeping Earth warm enough to support life. The most important of these gases are water vapor, carbon dioxide, and methane. Photosynthesis consumes carbon dioxide. Respiration and decomposition produce carbon dioxide and methane. For a long time, for hundreds of millions of years, vegetation and other natural processes have played a key role in balancing the amount of these gases that are in the atmosphere. But when we start to add new species like humans, our own actions push the system out of balance. The flux of gases in the atmosphere is no longer in steady state. So what do we do about that? One answer is that we might try a lot more trees and a lot less fossil fuels. 3 years ago, PG County Public Schools curriculum writers partnered with PRI to redesign the environmental science curriculum and to build in meaningful watershed educational experiences, MWEEs, as part of that curriculum. We chose to focus on the role of trees in the watersheds of Prince George's County. We centered the activity on trees for a number of reasons. For example, every schoolyard has at least a few trees, and also because trees provide an amazing array of ecosystem services. And anyone who knows me will know that I think trees are superheroes. There are loads of things that trees do in the natural environment. They provide habitat, increase biodiversity, and they provide a lot of services to human communities as well. Provisioning services like food, fuel, fiber, regulating services, controlling air quality, oxygen, carbon dioxide cycling, shade and cooling, cultural services like heritage, identity, recreation, art, beauty, and supporting services, nutrient cycling, water cycling. And trees are essential in the fight against climate change. Let's dive a little deeper into these ecosystem services. For example, plants control water flow and water chemistry. We've got 3 data sets here. On the left is precipitation and streamflow observations for the Anacostia River. The x-axis is time, showing average monthly data over the course of a year. The blue line is precipitation. The purple line is river discharge. Notice that the streamflow and rainfall are seriously mismatched, especially in the summer. When the rainfall is highest, the streamflow is lowest. How's that possible? The answer is the seasonal changes in vegetation. In summer, when trees leaf out, they transpire a lot of water, so much so that they intercept nearly all of it before it enters the river. On the right, we've got 1 week's worth of water chemistry data. On the top, dissolved oxygen, and on the bottom, pH. We see the daily change in dissolved oxygen as plants photosynthesize during the day and respire at night. We see the same diurnal signal in pH as CO2 dissolves in water to form carbonic acid. Let's also consider an example of how trees control the flow of energy. The graphic here is a satellite image of the parking lot at Ithaca High School in New York with surface temperature measurements superimposed. We see that the open grassy spaces around the parking lot have a surface temperature of 94 degrees Fahrenheit, while the shaded areas are 72 Fahrenheit, and the paved surface is a broiling 114. Clearly, trees are the key temperature control in this space. With that background, let's briefly look at the elements of a meaningful watershed educational experience and the particular elements of the Watershed of Trees MWEE in the environmental science curriculum in PG County. A meaningful watershed educational experience consists of 4 essential elements: issue definition, outdoor field experiences, synthesis and conclusions, and a culminating action project. For the Watershed of Trees MWEE, we've established a driving question. Within a human-dominated watershed, what is the impact of trees on water movement, energy movement, and the creation of microclimates? And how do these processes influence the quality of life for human communities within the watershed? With that driving question, we've designed a common experiment for all students to perform. At each school, students select a pair of field sites, one in an open sunny space and the other shaded. 3 or 4 times across the school year, they make the same set of measurements at each site: air temperature, relative humidity, dew point, and heat index, ground surface temperature, a soil temperature profile at 2 centimeters and 20 centimeters depth, and a soil moisture profile. They'll upload their observations using the district-wide data portal. These are 3 of the instruments that the students will use: the infrared thermometer for their surface measurements, their soil thermometers, and the sling psychrometer to measure air temperature, relative humidity, and dew point. We're going to go outside now and use the instruments, and then we'll come back and discuss our observations. So we've chosen a sunny and a shady site, and we've measured the air temperature, surface temperature, soil temperatures, and calculated the relative humidity. There are videos available to help students make these measurements and to understand what these data might tell them about the environment of their school. The videos are linked to the project website, accessed here with the QR code. Let's talk about relative humidity and evaporative cooling. When water undergoes a phase change from liquid water to water vapor, energy moves out of the system and the temperature of the system is lowered. This is the way human bodies cool down. We sweat to lower our skin temperature. The ability of water to evaporate is controlled by the amount of water vapor already in the air, the relative humidity. If the air is very humid, it's very difficult to cool down by sweating. To better understand relative humidity, we'll look at the psychometric chart that comes with the student sling psychrometers and how the wet bulb, dry bulb, humidity, and dew point are related. We'll take a look at part of the relative humidity video here. Let's calculate relative humidity, dew point, and the heat index. Let's take a closer look at the sling psychrometer and particularly what's happening with the wet bulb thermometer. The little sock holds a small reservoir of water around the thermometer bulb. When liquid water is in equilibrium with water vapor in the air, there's movement back and forth between the liquid and the vapor, and those rates of evaporation and condensation are exactly equal. These molecules are always in motion. Their motion and vibration reflect their kinetic energy. If the system is not in equilibrium, then there's a net transfer of liquid to vapor by evaporation or vapor to liquid by condensation. For example, after dunking the wet bulb in water, it's soaking wet and way out of equilibrium with the surrounding air, so evaporation exceeds condensation. When there's excess evaporation, energy is transferred from the liquid to the vapor. This loss of energy from the liquid lowers its temperature. Evaporation will continue until the system reaches a new equilibrium. We see that with the wet bulb temperature, which is lower than the temperature of the dry bulb. We're going to use the sling psychrometer to make measurements in 2 different locations. This one, which is forested, has a lot of vegetation, and so let's get the little sock wet. Our first field site is in the shade, and here we'll begin with the sling psychrometer. We'll measure the wet bulb and dry bulb temperatures and record those. Whirl this around for about 30 seconds and see how we do. Then we'll use the infrared thermometer to measure the ground surface temperature and record that too. When we look at the data, remember that the dry bulb is just the air temperature. Notice that the field site where I'm working, all 3 of these temperatures are different. We'll go to 2 other sites, repeat the measurements, and then work through what these temperatures mean. Which is obviously really open space. Get our sock wet, and because it's a little bit sunny, I'm going to have to try to shade the... When we compare the first 2 sites, we immediately notice that all the temperatures in the sun are higher than those in the shade. That's not surprising. And we could stop there and say, okay. But when we measured the wet bulb temperature, we've given ourselves information about water and about energy, and that allows us to gain a lot more insight from these data. But everything we've measured so far is invisible. Let's begin by constructing a physical model that we can see and then relate that to temperature and humidity. Here are 4 little containers of different size, and we're going to fill them up with colored water. The largest container has the most water and the smallest one has the least, but each one is holding the maximum amount of water for that container. It's 100% full. We can show that with a curve that relates cylinder size and water content. Now, let's fill the containers half full, or 50% of their capacity. We can also draw a curve showing where 50% is. And in fact, we could do this for any water level. Okay, now let's think about water vapor in the air. We'll make a similar graph, this time with temperature on the horizontal axis, moisture content on the vertical axis. The dew point curve maps the combinations of temperature and moisture where the air is 100% saturated with water vapor. At the dew point, water vapor condenses to liquid. We might see that as clouds, fog, rain, or dew. Notice that as the temperature increases, the maximum possible moisture content of the air also increases. Most of the time, the air around us is going to be in this area underneath the curve, where water vapor in the atmosphere is less than its maximum. We can also map out the places where the air has less than the maximum moisture content. Like our physical model, let's look at a position halfway to the dew point. For example, where the temperature is 70 degrees Fahrenheit and the relative humidity 50%, that fraction would plot here. That means the dew point would be 50 degrees Fahrenheit. The dew point is also directly related to the actual amount of water in the atmosphere. The higher the dew point temperature, the more moisture. For any temperature, when the relative humidity is 50%, we can mark that position halfway between 0 and the dew point. And we can draw a line that represents 50% relative humidity at any temperature. And we can do the same for any relative humidity and make a series of curves for different values of relative humidity. Now we have a graph with 3 properties that are all related: air temperature, the dew point or moisture content, and relative humidity. To tie these properties to what we're experiencing right now in the real world, we need one more thing: the wet bulb temperature. The lines representing wet bulb temperatures cross across the other 3 sets of lines. So now we have a graph that has 4 things on it: dry bulb and wet bulb, which are the things that we measure, and dew point and relative humidity, the things we want to know. Students may notice that the relative humidity is different at their sunny and shady field sites, even if they're not very far apart. This is because for a given moisture content, the relative humidity is controlled by temperature. If the temperature changes from sun to shade, the relative humidity must change as well. If we look at weather data, we can see that these changes occur nearly every day. The data here are from the continuous environmental data loggers installed at the Schmidt Outdoor Education Center. In the spring of 2024, we installed 2 sets of environmental instruments, one in the sunny field and the other 100 yards to the south in the forest. All right, this is Alex and this is Donald, and this is the new autonomous environmental monitoring station at Camp Schmidt. The instruments measure the same parameters that the students measure, and they're available online to help students place their own measurements in a regional context. Here's another example of data collected at the pair of sites at Camp Schmidt. This is 1 month of temperature data. The orange data points are air temperature at the sunny site, and the blue points are the air temperature at the shady site. We can see that the sunny site is almost always warmer. We see that more clearly if we subtract the shady from the sunny measurements and look at the difference, shown in green on the bottom of the graph. The maximum difference each day is marked by the green circles. The mean temperature difference between the sunny and shady sites is 16 degrees Fahrenheit or 9 degrees Celsius. Clearly, trees have a cooling effect on their local environment. And in fact, that cooling arises from 2 different properties of trees. About 2/3 of the cooling comes from the shade cast by the trees, while 1/3 is from the evaporative cooling as trees evaporate water through their leaves. We can do a very simple experiment to show how plants pump water. Here are 3 jars, each initially filled with the same amount of water. The jar on the left has several basil plants in it, the others are empty. After 3 days, the water level in the jar with the plants is significantly lower than the 2 control jars. Plants are water pumps. And they're a key link between water, energy, and climate. We can see the same effect if we look at regional data. In nearby Washington, D.C., we can compare the surface temperatures across different parts of the city. These are infrared temperature measurements showing how the trees of Rock Creek Park are a cool spot within the city, while paved city streets are significantly hotter. We can use the measurements that we've made to calculate the heat index. Here we use both the temperature and the relative humidity to determine the human health hazard that arises from both high temperatures coupled with high humidity. We've got some handy tips to help students collect good data and to help them care for their equipment and to make their data useful to other users across the district. Finally, when students have done their fieldwork, it's important to upload the data. This is how we gain a picture of the climate conditions across the entire county. Access the data upload page with the QR code here. And new this year, we're working with the FieldScope program to display the students' data in a more meaningful way. That project can be viewed here.